So we'll wait for a few more minutes. Shraditya Venkatramani, can we wait for a few more minutes?
Yes,
Sir,
it's good.
yeah. Shall we wait for a few more minutes because the participants are joining now?
Yeah, for sure.
Yeah, we'll wait for a few more minutes. It's just 4:40. Good evening, sister.
Good evening, ma'am. Good evening.
Shall we start, sister? Or shall... Kavita, ma'am, are you ready?
Yes, ma'am.
Yeah. So we can take permission from our administrator and we can start the program now. Yeah. So because let the participants keep on joining, but we will
Okay.
commence the program as per our timing.
Okay, ma'am.
Yeah. Kavita, ma'am, are you ready?
Yes, ma'am.
Yeah, ma'am. Start the program, ma'am. You have to moderate it. Start the program. Sister is waiting.
Okay, ma'am.
Yeah.
Okay, ma'am. Okay.
Yeah.
Yeah. Good evening, all. Happy to meet you all again for the second session of the international webinar, Recent Trends in Physics, organized by Department of Physics with CA, St. Joseph's College, Arts and Science, Chennai. In pleasant evening, it is our sincere effort to share with all the faculty across country the recent trend in physics. The vibrant resource person is here to share his knowledge and the area of his research to all the participants who have joined here. To commence this session with a prayer, I invite Reverend Sister Dr. K. Sandhya Kumari, Administrator, St. Joseph's College, Arts and Science, Chennai. Over to you, Sister.
Good evening, friends. The true compassion is born out of sacrifice. Our loving Father, we praise and thank you for this pleasant evening. Thank you, Lord. Though many people are suffering in this world due to the coronavirus, and we are able to participate because of your great support, your great help. Thank you, Lord, for giving us this wonderful opportunity. As we gathered here, enlighten us, enrich us, so that we may be able to participate in this webinars meaningfully. We also ask you to bless those who are organized this program. The head of the department, Mrs. Vijayalakshmi, and all the staff members, the Department of Physics with the computer application. We also ask you to bless our principal, Dr. Ruben, vice principals, all the staff members, especially the resource person who is going to enlighten all the participants in the term of staff and the students. Lord, once again, I ask you to bless everyone who are going to listen. At the same time, we also ask here graces and blessings to the people, those who are affected by this COVID-19. All of them get recovered and get a new life. For this we ask through Christ our Lord. Amen. Once again, good evening all.
Good evening, sister.
Have a wonderful time.
Yeah,
Thank you.
Sister. Sister, I am happy to introduce our resource person of the day, Mr. Aditya Venkatramani. So, sir, we have here our administrator, Reverend Sister Dr. K. Sandhya. She's the administrator of our college. She's here with us. Yeah.
Hello.
So I would have introduced before itself. So, sorry for that. Thank you, sister.
Thank you, ma'am. Thank you.
Yeah. So we also have here our principal, Dr. R. Ruben, here with us. So sir is also here. So welcome, sir.
Hello.
Yeah, I hand over the moderate MC to Mrs. Kavita. Kavita, ma'am.
Yes, ma'am. Thank you, sister. Thank you for blessing, sister. It is our earnest duty to welcome all those who have joined us today evening. May I now invite my head of the department, Mrs. B.V. Vijayalakshmi, to welcome all.
Yeah,
Over to you, ma'am.
Yeah, thank you, ma'am. So very good evening to all the participants. Welcome the challenges and look for opportunities in every situation to learn and grow in wisdom. We at St. Joseph's College, Arts and Science, Kovur, Chennai, Tamil Nadu, India, we believe in that. This pandemic has made us look above the challenges and create platforms to learn. All this has been made possible because of the encouragement provided to us by our management. I thank and extend my sincere welcome to our ever vibrant administrator, Reverend Sister Dr. K. Santiago Mary, for this webinar. I also deem it my pleasure to welcome Principal Dr. R. Ruben, who has steadfastly supported us always. We are made for goodness, friendliness, and humanity. We are to show that nothing can break our spirit and togetherness. This has been made possible in this session because of our resource person. I thank and welcome the young and dynamic researcher and the resource person of this session, Mr. Aditya V. Venkatramani, the research scholar, Harvard University. He has graciously consented to share his knowledge and expertise to the faculty across the country during this time. We welcome you, sir. I also welcome the members of Internal Quality Assurance Cell, Mrs. Vedavalli and Mr. Beski, for this international webinar. I also welcome Mr. Jayachandran round the clock.
Hello, ma'am.
Ma'am, can you hear my
Ma'am,
voice?
ma'am,
Oh,
it's not audible, ma'am. Yes.
good evening to everyone. To introduce the resource person, I'm glad to introduce the resource person, speaker of this session, Mr. Aditya Venkatramani. Our speaker is a research scholar who is pursuing this research at the Harvard University under the guidance of Professor Mikhail Lutin from the Harvard University, who is member in the National Academy of Science, and Vladan Ulichik from the Massachusetts Institute of Technology. As a bright student for his school days, his interest was always on research in physics. His alumnus of the National Public School, Bangalore, Karnataka, has received his undergraduate degree in physics and applied mathematics at the University of California. Currently, which are ranked among the top 10 universities in this world, Mr. Aditya V. Venkatramani, intrigued by the vast extent of the unknown in the biological systems and development of biophysical tools, was working on the quantum optics and atomic physics in his graduate study, which was research work at Harvard University. The resource person work now at the present focus on the creating strong interactions between the photons, which are the single quanta of the light. The researcher, Mr. Aditya V. Venkatramani, and his team are able to create the exotic states of the light, including the molecules of a photon and the repulsive photons with indicates of the crystal structure. May I now invite him to deliver is a talk on the field of quantum optics and the research at a single photon level. Over to you, sir. Welcome, you, sir.
Hi, thank you for the introduction, and thank you all for coming. And let me present my screen first, actually. Can you all see my screen?
Yes, sir. It's visible.
Perfect. Great. Yeah, thank you all for coming. It's amazing that I'm able to present this halfway across the world at 7:30 in the morning for me. But I'm sitting in this town in the northeast of the US, Boston, where I hope everyone is staying safe with COVID. But I guess one thing that's come out of this is that we've had everything turned digital. And because of that, we were able to communicate with people all around the world easily. In Boston, it's a nice little town just above New York. And it has a lot of different weathers here for people who are not familiar with the cities out here. It can be very hot and humid in the summers. Right now, the humidity is 95%. It's very, very humid right now. But once you go into autumn, sometime in September, October, all the leaves turn into beautiful colors, and you can see these kind of trees with red, yellow, green colors all over the place. And then they all fall away, and then in the winter, everything becomes snowy and white. So that's where I'm calling from. And I'll talk to you a little bit about quantum optics. And my aim for this talk is to have it at a very general level. And if by accident or by habit I use any jargon, feel free to post in the chat or interrupt me in the middle so that I can clarify what I mean, because by force of habit, I could use some terms that I don't really explain. So it'll be good if you have any questions, just let me know right away. And another objective that I have for this is to describe this at a very general level and also introduce what the state of the art current research is so that you have an idea of where this field is going and what people are working on, not just me personally, but also in the community around the world. So when people think about classical light, also I'm assuming most of you have some sort of physics background. If there's anything, again, just please let me know and I will try to clarify that. So when you think about classical light, most of it can be understood from just thinking about it as waves traveling in space and time. You can have electric fields and magnetic fields that are oscillating, and these are described by Maxwell's equations. And most of the physics of light that we see around in the world can be described by just thinking about it as waves propagating in space. And once you think about the waves of light, you can have many, many phenomena that can be explained just by that one simple concept. So you could have phenomena like diffraction, which is essentially you have light that gets scattered away from a tiny aperture. It could be a hole, it could be a slit, a lens, what have you. And you get diffraction, which is essentially the light spreading out. And you could also have phenomena like interference, where you have two waves that mix with one another, and then you could have them adding up or subtracting, and then you can get these patterns in space that are periodic, just because the light is superposing on top of each other. And of course, there's also things like refraction that some of you are familiar with, is light bending when it travels through media that's not just air. One thing that's common in what I mentioned so far is all of them can be thought of as linear optics. What I mean by linear optics is that the output of two waves superposing is just a sum of those two. So it's just a linear addition of whatever waves are superposing on top of each other. So most of the physics that we see around us can essentially be understood as linear optics of wave phenomena. But then you could have strong light matter interactions, and that happens once you have much more intensity in your light. And this was very difficult to observe in the past because it's really hard to get such high intensities enough to be able to observe these nonlinear phenomena. And this changed quite a lot about 100 years ago or so when people invented lasers. So lasers are amazing because you can get focused beams at single frequencies with extremely high intensities. And once with the invention of lasers, people could start seeing nonlinear effects with light. One example of that is second harmonic generation. Second harmonic generation is, for example, you have light at a certain frequency and you input it into some nonlinear medium. And what you get out is something that's double the frequency. So actually, this is a picture that I took in my lab. You see this deep blue light, which is at 480 nanometers. And the way we get this 480 nanometer light is take 960 nanometer light, which is in the infrared, and you actually can't even see it. And then you pass it through a crystal. And if the conditions are right, then the crystal, from the output of the crystal, you will get double the frequency, and we see this blue light coming out. I mean, we use this blue light to talk to the atoms, but maybe that part of it I will come back to much later in the talk. And the other kind of phenomenon, nonlinear optics. So this is second harmonic generation. You can also think of it as some frequency generation. So you have light at frequency 1, light at other frequency 2, and then you get output light at frequency 1 plus 2. Or you could have difference frequency at frequency 1, frequency 2, and then you can get the difference frequency 1 minus 2. So these kind of nonlinear processes are possible, but the caveat here is that you need large intensities of light, and you need to have these kind of nonlinear crystals. So when you think about optics in general, you can break it up into 4 major quadrants. So what I discussed initially is linear optics, where light doesn't interact much with itself, and then the photon number is also small. But also when the interaction grows a little bit larger, or then the intensity of light is high, which when the intensity is high is another way of saying the photon number is high, is you start getting classical nonlinear optics, like the second harmonic generations, frequency difference generation, and phenomena like that. Another thing I should mention is I'm using photon down here. That's a concept that I will again talk about a little bit. But so photon is a concept that is useful in the quantum mechanical picture of light, where you don't think about it as waves, but think about it as particles. And these particles of single quanta of light are called photons. And there's a duality between that. The higher the number of photons, the higher the intensity of light. But then what the interesting phenomena that starts showing up when the interaction of the photons start growing larger. So once the interactions of photons with matter start growing even larger, at low photon numbers, you start going into the domain of quantum optics. And for today, I'll focus a lot on this sector, which is nonlinear quantum optics, but at the single photon, a few photon level. And to really observe this, you need to have extremely high level of light matter interaction. And that's something that doesn't occur naturally in nature. It is also why we don't see these effects on a day-to-day basis. But right now, as a community in general, we have so much control at the single atomic and photon level that allows us to manipulate at the single quantum level, which allows us to interact, make photons and single atoms interact, and then you get quantum optics at the single photon level. There's another sector here, which is the many-body quantum optics. This is even harder because you need to have strong light-matter interaction, but also have that for many, many, many photons. So this field has been explored. It's still very uncharted territory. Not too many people have worked on this yet because it's an extremely hard problem. There have been really good progress there, though so far. For example, for anyone who's familiar with Bose-Einstein condensation, people have done that with atoms for quite a while now, maybe about 20 years. But the people have also shown in the recent past, maybe like 5-6 years ago, that you can get Bose-Einstein condensation of light. So this is a part of quantum many-body nonlinear optics. I will not go into that in that much detail in this talk. So now you can ask the question, okay, so it's great that we can study things at the single quantum level, but then why should we care about it? So I'll give you 2 reasons why. So one is from a technological perspective. So quantum computing right now is at least a very big buzzword, at least in the US, where what they're trying to do is use harness the power of quantum mechanics to make computations faster. So classical computers have limitations because once the problem size starts growing, some problems are exponentially hard with the problem size. But then in quantum mechanics, the hope is that this can be done much, much more efficiently because you could have states that can store information in parallel and process things in parallel. It's a little bit more complicated but that's sort of the general idea of why quantum mechanics can help. But then to use quantum computers, light becomes an important tool because let's say you have multiple computers, and right now we have networks that connect different computers. So even how I'm communicating with you right now is I'm connected to my Wi-Fi here, and then the signal is converted into light. It travels across the Atlantic under underwater fibers with these telecom fibers at 1550 nanometers and reaches you all the way across the world. So if you build a quantum computer, you need also similar communication devices and channels. And light becomes very important to establish and create these communication channels. So there it becomes very important to be able to understand light-matter interactions and control light at the quantum level. So that's why quantum optics is useful for quantum information and communication. Metrology is when you try to make sensitive measurements of whatever variable that you want using light. So one example of that is atomic clocks, for example. So atomic clocks can be made extremely precisely. So right now, state-of-the-art atomic clocks are so good that it loses 1 second at the age of the universe. So it's extremely, extremely precise. It's orders of magnitude more precise than current state-of-the-art clocks that are out there. But then if you use quantum light, it can be shown that this can be made even better. And the reason why we would care to make it even better is to study phenomena across the universe. If you want to measure stars and galaxies and black holes way back out in the universe, you want to have time precision that's extremely good. And also another application for human uses are improving GPS and making resolution of coordinate systems much, much better than it is right now. Then the other reason why quantum optics might be interesting to study is for fundamental physics sake, trying to understand light-matter interactions better and also just have fun with creating exotic states of light. So I'll talk a little bit about it and the sort of stuff that I work on and I worked on in the last 4 or 5 years is once you make light particles interact, you can, it says the PPT is not seen. Is it still the case?
Yeah, yes, sir. The PPT is not seen.
Oh, okay. Let me try presenting it again.
Yeah.
How about now?
No, sir, it's not seen. Yeah.
Okay.
It's visible. It's getting visible.
Is it good now?
Yeah, yes, sir. It's done. It's visible now.
Okay, great.
Yeah, thank you.
Great. Yeah, so yeah, we can make, once we make light particles interact, you can make exotic states like molecules of photons or crystals of photons, and I will talk a little bit about how that works a little bit later. But yeah, you can have fun with creating these exotic states of light, and then this can in turn be useful for these technological applications that I just discussed before. And there was a question, is susceptibility change across polarization?
Yeah, so question and session, question and answers, we'll moderate in the end, sir. It will be moderated by the host.
Sure,
So
sounds
we'll
good.
take note of the questions and we'll moderate the question
Okay.
and answer at the end of the session. We'll continue with
Okay,
the
sure,
session.
sure. Yeah, I was just keeping up for any, I need to pin my presentation. How do I do that? Is that pinned? Okay. Yeah, just let me know if there's any issues along the way. Okay, so now that we have some sense of why this is an interesting problem, the question comes down to why has it been so challenging in the past? So one is, of course, that I mentioned that the light-matter interaction is weak. And to emphasize how weak that is, let's say you take light and then you take a single atom. The absorption of light with a single atom can be very, very small. It's typically much less than even 1%. So, which means that if you take light, a single atom, the effect of a single atom on light is insignificant, which means that you see some average effect, but you really don't see it at the quantum level just because the interaction strength is extremely small. So the physics where photons matter is when there are significant interactions between single photons and matter. I'm sorry, I just couldn't resist putting this pun in this slide. So there are multiple solutions to doing this. I will talk about a few methods here. There are more ways to do it, but the general idea is that you somehow really want to enhance the probability that a single photon and a single atom will interact strongly with one another. So one idea is to put a cavity. So what I mean by a cavity is take two mirrors that are facing back to back with each other. And what a cavity does is that because they're two mirrors, light will bounce back and forth, ideally infinitely many times. And many of you might have seen this when you have two mirrors and then you see many, many images of yourself. And it's a very common, fun game to play. Of course, it's not really infinite because light slowly leaks out of the system. So there's finite number of times which it goes back and forth. You could have cavities right now, state of the art, that can do this hundreds of thousands of times, million times, or even higher, depending on how you fabricate the system. But then what happens is that because the probability of the atom absorbing the light in one round trip is small, but then if it bounces back many, many times, it enhances the chances of interaction just by doing this multiple times. So what effectively happens is that the probability of the light interacting with the atom goes up significantly. And once you have this atom being the light being absorbed by the single atom with a high probability, then you start seeing quantum effects. So before I talk about what sort of effects you can see, let me just, to give you a sense of what these devices actually look like, I will maybe give you a few examples of different platforms that have been used, and also what is quantum electrodynamics. So QED is quantum electrodynamics. So cavity QED. So you take electromagnetism and then you quantize it and you start seeing the quantum effects. So which is what I mean by there. So the first example here is essentially just two optical mirrors that are mounted on these aluminum fabricated devices. And then you can move the distances between them, and then you can control the reflection properties of the light and the mirrors. The middle example actually is not an optical mirror, but a microwave mirror. And a microwave mirror is essentially just a resonator that a microwave light can live for a long time in. So that device is actually fabricated by IBM. And then the one on the right is a nanophotonic crystal cavity, where what you have is it's a nanofabricated device which have Bragg reflectors in them. And once you send light, it can reflect back and forth and live for a long period of time. This is actually a very cool experiment. Actually, a friend of mine works on this. So what they do in this experiment is, if you see out here, there's a fiber that is attached to this crystal. And then the light comes down the fiber, and then they trap one single atom above this crystal, and then they can study light-matter interaction between the single atom and then the light bouncing off the nanophotonic cavity. So these are these are different kinds of platforms that exist. These are not exclusive. There are many, many more ways of doing this, but this gives you a general idea of the different kinds of platforms that you can use to make a cavity and then have strong light-matter interactions. So now to discuss a little bit about what kind of physics you can do with it. So one example of it is getting something called a squeezed state of light. So when you have light from the Heisenberg uncertainty or just from Fourier transforms, it turns out they're actually equivalent, is you can show that you cannot know position and momentum or the electric and magnetic fields together simultaneously with high precision. So once you, and because of that, you could have uncertainty that generally tends to be symmetric in like momentum and position. But using nonlinear interactions, what you can do is squeeze one of the axes, which means you are taking the uncertainty in one of the axes and putting it to the other axis. You still have the same Heisenberg uncertainty, but you can reduce the noise in one direction much, much smaller than what the quantum predicted noise is. And this can be very useful because let's say you want to do some measurement. The noise provides a fundamental limit of how precisely you can do measurements. But if you can squeeze the noise along one of the axes, then you can do much, much more precise measurements along that axis. So people use squeezed states of light to do metrology. So this is going back to what I said before, is quantum optics can be used for measurements and like atomic clocks. So having squeezed states of light can be used for these kind of applications. This is something also I worked on during my undergraduate days. Actually, so this example that you're seeing here, squeezed light, is actually not of optical photons, but of microwave photons. So we actually used microwave resonators and some nonlinear element in microwave resonators to create this squeezed light. Another example of where quantum mechanical effects show up in cavity systems is, let's say you have a bunch of atoms inside a cavity. So this is now a regular optical cavity. And let's say you take a single photon, and a single photon gets absorbed in these atoms. And what happens is that when a single photon gets absorbed in these atoms, it changes the reflection property of this cavity. So you say you take this green photon, it gets somehow absorbed in these brown atoms, and then you send this orange light. And if there is no atom in there, the orange light will just go straight ahead. And if the photon is stored, then it gets reflected. So what you've effectively done is made a switch out of a single photon. And it's, if you think about it, it's sort of amazing because one single photon can affect the transmission property of a large classical field of light. So if you just take a minute to think about it to see how crazy that is, you need to have really high level of light matter interaction for that to manifest. And this is enabled by having this sort of cavity QED system.
Sorry, sir. Sorry to interrupt, actually. Somebody has presented and disturbed the screen.
Okay.
Prashant Nani, kindly do not present your screen. Sir, can you represent your screen?
Yeah, let me do that.
Because the PPT is not visible now.
Sure.
Because the participants, they are not supposed to present the screen. We request the participants. Sir, can you present your screen again?
Yeah, is this back?
No, your PPT is not visible.
Let me try. Oh, yeah, let me try that again. Now it should be visible. Great.
No, not yet, sir.
Okay,
Yeah, it's coming. Yeah. We'll wait for something. Yeah, it's visible now, sir.
Okay, perfect.
Yeah, thank you.
Perfect. Yeah, if you can see if there's a way to pin it, that would be great, because if someone accidentally presents, I think it's going off. So if there's some way to pin it.
Yeah, you can pin it, sir, actually. You can pin your screen so that people will not be able to disturb it, actually.
I have tried doing that.
Because from our side, because repeatedly,
in principle, it should be
participants from morning session onwards, we have been requesting the participants not to present on the screen. So once again, we'll place the request. Yeah, we'll proceed with the presentation, sir. We'll proceed.
Yeah, just let me know if it happens again and I can fix it.
Yeah, thank you.
So now I have been saying a lot of these effects are quantum mechanical, but now I'd like to maybe take a minute or two to discuss how do we actually know what is quantum? Right? So I've been sort of alluding to this fact, but not really being very explicit about what it means. So what is special about having an effect that is quantum mechanical is having correlations in your system that are beyond just probabilities adding. So what I mean by that is if you take a system where you can describe by some probability distribution, and a classical system, what happens is that you can just add these probabilities and then you get the net effect. But what happens in quantum mechanical system, and I think this is a key distinguishing factor of what makes a system quantum mechanical, is that probabilities don't add, but the square root or the amplitudes add instead. And that makes a big difference because you could have interference that doesn't exist in other kinds of systems. So I'll discuss one method in which you can quantify the quantumness of light. There are other techniques that I'll maybe mention, but this is one that I will talk a little bit about in detail. It's called G2 correlation function. It's a second order correlation function that you can use for light. There are other higher order correlation functions too. But the intuitive way to think about what a G2 correlation function is as simple as the following. So let's say essentially what it quantifies is the likelihood of observing a second photon once you observe a first photon. It's as simple as that. But then this has a lot of consequences in quantifying what a quantum system is. So you can show that if a G2 of 0, when I say 0, I mean the time difference between photon 1 and photon 2, if that likelihood is less than 1, which means they're anti-correlated to arrive at the same time, it is quantum mechanical. And another criteria is that G2 of 0, where photons arrive together, is less than G2 of tau, where tau is any time between 0 and infinity. That is also quantum mechanical. You can actually very easily derive this. It's a fun exercise for anyone who's interested to derive this from just the definition of the G2 correlation function, which I have actually not put here. I've tried to avoid equations as much as possible and have intuitive explanations. But if you use the definition of G2 and use very simple Cauchy-Schwarz inequalities, you can derive these expressions. And you can show that this only works if you have a quantum mechanical correlation and not classical probabilities. So as an example, this is actually some data that I picked up from one of my papers, is a G2 correlation function that is evidently quantum mechanical. So you can see G2 of 0 at time 0 is much less than 1. And it is increasing as time, so which means G2 of 0 is less than G2 of time for time greater than 0. So actually, it'll be fun to think about what this actually means. So if you use the interpretation that G2 is a likelihood of observing a second photon given you saw first photon at time 0, you can see that at time 0, it's unlikely that the second photon is arriving. And after some time, maybe 100 nanoseconds later, there is more likely that the second photon will arrive. So this actually is a precursor to what I'll describe later is single photons pushing each other away. So you get repulsive interactions between photons. This is just a precursor to what I will mention later. I will talk a little bit about repulsive photons more a little bit towards the end of the talk. So this is a G2 correlation function that can be used to quantify whether what you're seeing about light is actually quantum mechanical. There are other ways to do it. There are tomography methods. There are also representation functions that you can use, these quasi-probability distributions. So when I showed the squeeze state of light, what I implicitly assumed is some sort of quasi-probability distribution. And you can show that in certain kinds of these probability distribution functions, if it's negative, it can be quantum mechanical because in classical probabilities, it doesn't make sense to have a negative probability. But in quantum mechanics, that is in some sense allowed. So the first method we discuss is the cavity method, where you essentially have the light reflecting back and forth, increasing the probability that a photon or light can be absorbed by a single atom. Another method, which I'm going to propose here, is to use multiple atoms, so use a lot of material. But then at the outset, this seems a little bit strange because this is something we see day-to-day basis. You have light traveling through a piece of glass, and a piece of glass has 10 to the 23 atoms. So why don't we see quantum mechanical effects? And that is true because what will happen is that if you just put a lot of material, it doesn't make a difference because the effects just linearly add up. So it doesn't really make that much of a difference. But of course, the reason I'm presenting it is because you can actually make it work. but you need to do something special to make it work. One idea that you can use to make it actually quantum mechanical is to coherently couple photons to matter. So what I mean by coherently couple photons to matter is that you say you take some light and it gets absorbed by the material. But when it's coherent, what happens is that at some later point in time, you can convert that back into a light and send it back out. So let's maybe walk through this process again. You have some material, you take light, the light gets absorbed in the material. Generally, what happens is that once it gets absorbed, it just is lost. It goes as heat, it gets scattered out. You don't know what happens to it. But if it is done coherently, you can convert this light back into traveling waves, and then it can emit out of the medium at some point later in time. There are many ways to do this. I will not talk about how this is done, but just take my word for it that you can actually do this. We do this actually every day in lab, and it is possible. But one way to think about how this happens is to create a new kind of quasi-particle. So when the light gets absorbed by these atoms, you can create this quasi-particle called a polariton. So let's discuss about what is a polariton. You can think about polariton as just some superposition of photon and matter. So it's a particle that is partly photon and partly matter. So it's not an atom anymore. It's not a photon anymore. It's a hybrid between the two of them. And it's interesting because it moves like light. So it moves forward in space. It has some velocity. But the interesting thing is it also acquires the properties of matter. So it can become massive. So you can have something, a traveling wave that actually has a mass. But it can also interact like matter. So any interaction that atoms can have, like electrostatic interactions, dipole interactions, what have you, can be imported into a polariton. So you can have features of both. And this particle can then be converted from photon into polariton back into photon. And so now if you go back to thinking about how using a lot of materials help, once you create this polariton, then the light can then be absorbed into the material, create a polariton. The polaritons can then interact through the atom and then come back out as light. And that's how you can create strong interactions between light. So by engineering the coupling between the photons and the atoms, you can tune the interactions between the photons to be attractive as one example. So you can have two photons that over time pull each other together. So you can have photons that attract one another. And this has a very interesting consequence, actually. So once you have things that are attracting one another, you can have molecules, because essentially what happens is that you have photons that are pulling each other together. Then they can attract and then bound itself together and form a molecule. There's also some experiment that I worked on a few years ago. So what you're looking at here is actually a G3 correlation function. So I introduced a G2 correlation function before. A G3 is three-dimensional extension of that, or three-particle extension of that, but the idea is similar. It just tells you the probability of a likelihood of seeing photons 1 and 2, given you saw photon 3 at some other time. And what you see is that the blue regions here are uncorrelated photons, so photons don't care about each other. But the yellow and the red sections indicate that the photons are bunched together, which means that the photons are more likely to appear together. And there are indications here that show that in the center, when three photons are stuck together, you can have three photon molecules where three photons essentially bind together. Or you could have these sectors where two photons bind together. And all of this is arising just from the photons attracting one another through this engineering between atom and light coupling. And by also modifying these interactions, you can make them repulsive in the sense that the photons cannot start push each other away. So you could have photons that are close to each other, and then they push one another away from each other. And this is something that I talked about a little bit before. Is this, when I showed you the G2 correlation function before, we saw that the light was more likely to appear at a later time, and then they push each other away. And if you do a three-particle extension of this, you can start seeing that the light, because they're pushing each other away, start periodically arranging one in a linear pattern. So if you take the many-body extension of this, you could have light particles that are equally spaced in time and space, which can be then thought about as a crystal. So people are very familiar with crystals of atoms. All these gems and diamonds are essentially just crystals of atoms spaced periodically in space. But an analog of that is having single particles of light, these photons, which are arranged in space to create a crystal of light. So what I really want to convey of what I described so far is that we have really good control of photons and materials at the quantum level, like at a level that has been unprecedented. And this is something that's been developing over the last 2 or 3 decades, is we have really good control of having strong light matter coupling. We have really good control of manipulating atoms or material at the single atom level, coupling them to single photons or a few photons and controlling their interactions. And now with this, it opens up a lot of avenues. One is, of course, that we have such a good understanding, we can use that to do quantum engineering and use this for quantum technologies, where, like I discussed before, we can make these networks of quantum systems and have many quantum computers that are communicating with each other using quantum light. Or you could have all optical quantum devices. You have optical switch. I gave you an example of an optical switch using this cavity quantum electrodynamic system. And you could have, if everything is all optical, it is ideally maybe faster because light travels much faster than electrons right now, which can hopefully make faster computers and also can maybe make things more energy efficient. So there's a lot of avenues for quantum technologies once we can establish and control these strong light matter interactions. But it also opens avenues in fundamental physics, because now that we have strong interactions, we are at a level that we've never been before in the past, which allows us to create these exotic states of light, like crystals of light, molecules of light, that has never been done before. And the next step forward is really take this to the many-body limit. So this is the sector in the quantum optics diagram that I showed before that I didn't really talk about too much, is the many-body optics part of it, is mostly because that's very uncharted territory so far. So people have done Bose-Einstein condensation, but once you put strong interactions, there are avenues to doing much, much more. We just don't know what exists out there. So it's an avenue for using these technologies and using these light matter interactions to explore what happens to many-body physics of just photons interacting and see what happens there. So with that, that's the end of what I had. Thank you for your attention. Let me know if you have any questions.
So thank you, sir. Thank you for the wonderful session. Actually, the chat box is with all complimentary messages, and also we have few questions there. So can I start moderating the questions?
Yeah.
Yeah. So probably I'll start with the last question as the first question now. We have one question from Ms. Swati Mukherjee. She would like to know, can we use Polariton in optoelectronic devices?
Yes. So yes. So optoelectronic devices are essentially you have light propagating through fabricated electronics or fabricated optical materials. And people have shown polaritons there, mostly with weak interactions, not as strong as cavity QED systems or the ones that are described here. But it's definitely possible. And once you make polaritons, they're actually a key feature in optoelectronics that I didn't quite mention here is the existence of solitons. Solitons are waves that propagate through a medium without getting dispersed, which means if you send a wave packet, the shape of the wave packet stays the same. And if you use polaritons, you could have wave packets that are at the single quanta level propagating through these materials without dispersion. And that is useful, very, very useful, actually, if you want to do long-range communication, because you don't want your wave packet to spread over space.
So thank you, sir. Probably she got the answer. Now we have one question from Mr. Raj Kumar. He has, in fact, 3 questions, and I have combined all the 3 questions. So what is the difference between linear and non-linear medium?
Right.
Is this question you want to combine all the 3 questions and ask you? Or
let me answer that. Let me answer the first one. I think that's a very important question for what I've presented so far. A linear medium is essentially when you have, say, light wave with some amplitude A and some light with amplitude B. The output is just proportional to A plus B, which means 2 will sum together, and the output is just proportional to the sum of them. So that's a linear medium. Nonlinear medium is when it's not proportional. So when you have something that's, say, the square of the 2 waves that come in, or some other function that is not just sum of those 2. So when you have, as an example, when you have this second harmonic generation that I mentioned for nonlinear medium, if it's linear, if you send frequency 1, only frequency 1 will come out. But in this case, we have frequency 1, frequency 2, and then somehow add together and then give a new frequency, which is different from what you input. So that becomes a nonlinear medium.
Yeah. So, say second question is, what is Polariton? Probably, I think he must have got the answer from your session, but would you like to explain it again, sir? What is Polariton was the second question.
Yeah, so I can very briefly reiterate that. So Polariton is a quasi-particle. So when I say quasi-particle, it's not a real particle of nature, but something, it's an excitation that is a hybrid of whatever natural particles there are. So here my natural particle is an atom and a photon. And the quasi-particle, what it does is that it combines those two and then behaves like a new hybrid system. And that's what a Polariton is.
Yeah, so thank you, sir. The third question is, what is the relation between nonlinear and quantum optics? Nonlinear optics and quantum optics.
Right, so the line is sort of fine. So what I try to emphasize here is that nonlinear, what makes it quantum is when the quantum nature of light matters. So let me explain again a little bit of what the quantum nature of light matters again is. So when what I mean by quantum nature is that the photon nature of light starts to matter. So in nonlinear optics, all the physics can essentially be described by just waves. And you don't really need to invoke the presence of photons to describe any of the nonlinear effects. So that's what I mean by classical nonlinear optics. And when the photon strengths become large enough, then the discreteness of the single quanta of light actually starts to make the physics makes it important for the physics, and that makes it quantum.
Yeah, so thank you, sir. Now, one more question from Mr. Jawahar. Is susceptibility change along with polarization when light enters nonlinear material? Will the susceptibility change along with polarization?
Yes. So you could have materials. So you have birefringent materials where you have the refractive index that depends on the polarization or the angle of incidence. And you could have materials that do depend on that. It really depends on the crystal structure of what is inside, but it is definitely possible. And we do use that. Even for a nonlinear crystal, the polarization is extremely important. If the polarization is off, we will not get the second harmonic generation. So it is very polarization sensitive.
Okay. Thank you, sir. Now, Ms. Subhashini, her question is, what is the difference between nanophotonic cavity and ordinary cavity?
Actually, let me go back to the picture. That'll be helpful. Here. Yeah, so nanophotonic gravity tends to be much, much smaller. So the reason it's nice, actually, this is a very important concept to get, is the reason why you have strong light matter interaction in a cavity. One reason I talked about is light bouncing back and forth is one. Another thing I didn't really quite mention is to have a large single atom photon coupling. It depends on the mode volume of single photon. So what I mean by mode volume is that the volume that the photon occupies in space. So the smaller the volume is, the larger the probability of interaction would be. And it's sort of intuitive to think about it, because let's say you have an atom and the light is spread 10 times bigger than the atom, then only a part of it is going to interact. But let's say you make the photon smaller, comparable to the size of the atom, then the probability of interaction is going to become larger because the light is essentially all hitting the atom right now. So the mode volume is actually a very important figure of merit for these cavities. Nanophotonic cavities are fabricated using these dielectric materials. And it's important because you can change the refractive index of these dielectric materials to make the mode volume actually much, much smaller than you can get with free space mirrors that you just place, because you can change the refractive index of these dielectric materials. So you could have nanophotonic cavities that don't really have as many bounces back and forth as just two mirrors, but can still have very good single atom photon coupling because they can have much smaller mode volumes than that exists in just two mirrors.
Yeah, so thank you. So Mr. Jawahar has one more question. How can phase or field amplitude be controlled to get the squeezed lights?
How can phase? Yeah, that's actually a very good question. Yeah, no, I think I got that question. So it's actually a very good question. To explain that takes a little bit of details of how it works. So maybe I can give like a very high level answer to this. So the way you create squeeze light is you have some nonlinear medium and you have some light that you want to squeeze. But to activate this nonlinear medium, you generally have a pump light at some of the frequency typically that is pumping the system. I mean, you can control the phase of the squeezing by changing the phase of the pump light. That's like a very general answer, but I hope that gives you some sense of how that's done.
Yeah, probably he must have got the answer. He must be there somewhere in the participants. Now we have one question from Mr. Praveen Elias, but in the course of your explanation, I think he got the answer. But for the benefit of other participants, I would like to repeat the question again. Actually, light is a wave and atomic Actually, light is a wave and atom is a particle. So semi-classical approximation is the best way to handle the quantum phenomenon. But at the interaction of both the system, what kind of nature one could take, either particle nature or wave?
Right. I think the idea of particles and waves are good at the extreme limits. So what you said is exactly correct. Most of quantum optics can be understood by semi-classical approximations. So you assume, so it can go both ways actually. So you can assume quantum atom and classical light is one way to do it. You can also have classical atom. When I mean by classical atom, actually you can explain a lot of phenomena by just assume atom is essentially balls in a spring, and it actually works very, very well. Of course, there are caveats, but it's amazing how well that model works. And then you can have quantum light where you have discrete photons. So you can go both ways. It really depends on the problem you're working on, which approximation works better. Actually, for these single photon experiments with this repulsive and attractive photons that I discussed, the semi-classical approximation where we take the single photons, but then classical atom works better. Sometimes when you have this cavity QED systems where you say have a single atom and a single photon interacting, then you really need to take the quantum mechanical picture where you assume there are particles for both. When you talk about classical optics, you take the wave nature of the wave nature of light and the particle nature of atom into account. So it really depends on what kind of physics you're working with, and they're all applicable in different regions.
Yeah. There are a few more questions, sir. Can I take the questions? Will the time permit for us?
Yeah, of course.
Yeah. So one question from Mr. Sudhakar. Non-linear and quantum both are same or different material?
Yeah, so it is typically a different material because nonlinear material, even they are kind of hard to find in nature. They don't exist readily, and they need to be sort of specially designed. But then to make it quantum, you need to have interactions that are even stronger, which is even less likely to find. So you really need to be very, very careful about creating and engineering these systems. So yeah, they are typically quite different.
Okay. So we will take one question from our YouTube link, sir. Is there any device from quantum optics? From Joe Blessing. The question is there any device from quantum optics?
Oh yeah, so there are many. I can give you a few examples. So one is a single photon generator. So I all this while I emphasize that you can just create single photons, but it's actually very non-trivial to create one single photon. And the physics behind it is quite challenging. But it is possible, and you can buy commercial devices. They're quite expensive, but you can buy commercial devices where on demand, you say, I want a single photon now, it gives you a single photon. And that can be very nice. So that's actually something that is even out in the market. And people use these devices and build on it to create something called quantum key distributions. And this is also something you can buy off the market right now. And what these quantum key distribution devices do is that you can have two photons, but they're entangled with one another. What that means is that they have correlations that are quantum mechanical. And this can be useful for distributing keys. So when you have computer systems, when you have work with internet, a lot of it is encrypted, which means you need to have some key to decode the encryption. And it is shown that if you have quantum mechanical correlations, you can make things much more secure than current cryptography systems that exist in the current internet, which can be broken by a quantum computer. And if you have quantum encryption, you need these quantum keys, and you can buy devices to send these quantum keys to different places.
Yeah, probably we'll take two more questions, sir. So one question from Ms. Devi. Can you explain Kerr effect in NLO?
Right. So Kerr effect, for those who don't know what NLO is a nonlinear optics medium. And Kerr effect is a special kind of nonlinear effect. So when you have nonlinear effect, so let's say we have a linear medium. So when I say linear medium, it means that the response of the medium is linear to the input light. But then you could have higher order terms. You could have second order effects, third order effects, fourth, and so on to infinity. Most materials tend to be symmetric in structure, and the second order correction is typically zero unless you artificially create a system that is not symmetric or centric with respect to rotations. It is possible, but typically in nature, you don't get second order corrections. So the leading order correction after a linear response is the third order response. So what they mean by the Kerr effect is third order response of the material with respect to input light.
Yeah. So the one question from Deepika A. Pillai is Polariton stable or unstable?
Oh, that's an extremely good question. So there can be both. There can be both kinds of polaritons. And let me explain by what unstable and stable means. So let's go back to Polariton. So when I talked about photon and matter, I just said it's going to get stuck in the matter, and then we can take it out whenever we want. But that's not always true. Let's say we create a system where, or just take some average material and you shine light at it. The photons will just get absorbed or scattered. So unstable polariton, the chances of it scattering is more likely. So it gets absorbed, but then over time, slowly, it just decays away. So that's an unstable polariton. A stable polariton is when it doesn't really decay, it just stays in the same state. And another term for that, for anyone who's interested, is called a dark state polariton. And the reason it's called dark is just because there's less scattering out. And it's a historical term, but it's something that people talk about when they talk about polaritons, is a dark state polariton. And then the unstable is typically called a bright state polariton.
Yeah, so thank you, sir. Probably we'll take this as the last question. One from Ms. Sherin Vemuri. Is laser a polariton?
Not typically, but you can have lasing systems that do have polaritons. You could have atom lasers and light traveling as solitons inside, but I would not really classify that exclusively as polariton because the laser light coming out is just photons. But inside the lasing material, you could have light matter interactions that could look like polaritons because you have some hybrid, but it's maybe not the right picture to think about.
Okay, so I think one Mr. Prem Kumar, he wants me to include the question. So probably I'll take that up again as the last question. The epistemological interpretation at quantum physics valid? From Mr. Prem Kumar. Okay,
let me see what that question. I'm a little bit unsure what that question means. Can you remind me what epistemological means?
Probably Mr. Prem Kumar will be able to give us more clarification on that.
Let me try to look that up.
Yeah.
Okay, epistemology, for anyone like me who doesn't know what that is a philosophical term, which is a theory of knowledge, which is distinguished belief from opinion. Okay, this is an excellent question. And I have a lot of opinions on this. So it is very vague in the sense that quantum mechanics gives you things that don't seem very intuitive, but I would still take it as a scientific theory because it makes predictions that can be tested and verified. So it's not just an abstract theory, but something that is scientific in the sense that you can make concrete predictions and do experiments and verify that these predictions actually hold.
Yeah. So thank you, sir. So probably we will wind up the session now. So before I go on for a formal vote of thanks, I would like to thank the people behind this session. So we have our system admin who are working round the clock to make this event and all the program conducted by St. Joseph's College a grand success. And also I have my team IQAC, Mrs. Vedavalli and Mr. Beski, who has been supporting me in all the initiative taken by IQAC and also for the department. The session to Mr. R. Rajkumar for the formal vote of thanks. Over to you, Mr. Rajkumar.
Okay, thank you, ma'am. Now it's a time for vote of thanks. I deem it my privilege to propose the vote of thanks to all who have gathered through this platform. First and foremost, let me thank Almighty for giving us strength to keep going and doing the things. We love most sharing of knowledge during this time of pandemic. God has given us the another beautiful day to share, enjoy, and learn. I wholeheartedly thank our beloved administrator, Reverend Sister Dr. K. Santiago Mary, for the helpful wishful prayers and blessings. Thank you, dear sister. I also thank Dr. R. Ruben, Principal, St. Joseph College, Arts and Science, Chennai, Tamil Nadu, India, for his guidance in organizing this webinar. The dynamic resource person, Mr. Aditya V. Venkatramani, has taken time off his busy schedule to share the knowledge with all who has joined us today. Sir, your lecture and the way you have explained the concept, I'm sure, will kindle the interest in many here. The students who have attended this webinar would follow your footsteps leading to research in physics, particularly in the field of quantum optics. The scintillating world of photons will definitely enthuse us all. Thank you, sir. I also thank the head of the department and vice principal, Mrs. B. Vijayalakshmi, for her initiative in organizing this webinar. Also, I thank my colleagues, Mrs. Kavita and Dr. E. Chinnaswamy, and the technical team, Mr. Jay Chandran, and others. Thank you, dear participants. Hope you all had a happy learning today. Stay safe. All the best. Thank you.
Yeah, so thank you, passionate participants. And once again, I thank our resource person for the wonderful session. Thank you, Mr. Aditya Venkatramani, for sparing your time amidst all the busy schedule, because you are going to join your postdoctoral research again in a few months. So our heartiest wishes for that. So now I thank all the passionate participants. The feedback link has been posted. It will be there for another 15 minutes. We request the participants to submit the feedback link to get your e-certificates. The e-certificates will be posted to your registered mail ID. Thank you, and you all had a happy learning. Stay safe. Thank you.
Thank you all for coming, and thank you for inviting me again.
Thank you, sir. Thank you so much.